Hi, and welcome to the fourth lecture in the series, in which we will learn about computers and operating systems. After that, we will apply this knowledge to practical programming examples in assembler, C, Shell, and Python. It is best if you have a Linux terminal at hand to follow along the example. Computer's binary format. Due to simplicity and logical states being represented by voltages, the binary was chosen to represent the numbers. Unsigned integers. Most basic decimal binary representation is the unsigned version. No negative numbers. Decomposing binary and decimal numbers. In example, 9 in decimal is equal to 1001 in binary. If we decompose it, we can see that the base is different. In decimal we have 1, 10, 100 and 1000, and in binary we have 1, 2, 4 and 8, etc. Signed integers. To represent negative numbers we can use leftmost bit for the sign. These are called signed values. Of course, this changes the range. In example, from 0 to 256 to minus 128 to 127. If we break it down and look at the representation, we can see that the math still works. But if we do the arithmetics, it will not work. It also suffers from the double zero issue, as both 0 and 1000 represent the number 0. To fix the arithmetic, one's complement was invented. It inverts all the bits for negative numbers, except for the sign bit. In example, to convert minus 8 to 1's complement, we represent it in signed binary and then invert all the bits. Arithmetic will now work, but we have to carry the overflowing bit to the right. It also has the double zero issue. 2's complement. To improve the arithmetic and solve the double zero problem, the 2's complement converts negative numbers in 3 steps. First, convert to unsigned binary, then invert all bits, and then add 1 to the inverted number. In example, minus 8, we represent it in signed binary, then invert it, and then add 1. If you see the arithmetic, it will work. If we decompose the number, we can see that the math will still work, we just need to make the first base negative. Hex. Binary is usually represented with hex values, which accommodate for numbers up to 15 with letters A to F. In example, A, B, C, D, E, F represents the numbers above 10 and 10. Hex is usually denoted with a 0x prefix. In example, 99 in decimal is 63 in hex. We can also break it down to the base. If you look at the IP address example, we can see how we can save space with using hex. Of course, it's rarely that to use the binary. Again, we can see hex saves a lot of space when typing. The order from left to right or right to left in which the bits are stored depends on the computer. This is only relevant when working with low-level embedded programming or using uncommon architectures. Main computer parts. Memory. Memory consists of addresses and their values. If every address can hold 1 byte, 8 bits, a 32-bit address size can hold up to 2 power 32. Or around 4 gigabytes. Early systems had 32-bit memory addresses, while today's systems have a 64-bit. If you look at the memory, it's just an address and its value. Kernel keeps a part of memory for itself, and the other part for user space. In example, 1 gigabyte for the kernel, 3 gigabytes for the user space. This is done to limit the user's program's access to kernel resources and possibly crash or abuse the system. To inspect the memory hardware and current usage, we can use the following command. Some of them might be run as root. For example, ls hardware, hardware info, free memory, lsmem. Registers. CPU registers provide memory closer to the CPU, used for processing, caching, etc. Registers usually have the same value and address size as memory addresses, in example 32 or 64 bits. This way, they can hold a memory address for a CPU to operate on, as well as the memory values. As we can see, the address is 32-bit size, and also the value is 32-bit size. Word and address size. Basic characteristics of a computer are word size and address size. Word size describes the number of bits the CPU can process at a time. The register size, usually 32 or 64 bits. Address size is the number of bits for the memory address, usually also 32 or 64 bits. These values may or may not be the same. CPU. CPU executes an instruction on every clock tick, in example 2 GHz, on values stored in memory or registers. It can have multiple cores, where cores can have multiple threads. These are used for parallelism. We can see CPUs can have cores, they can have registers inside or outside, and they can use the memory. To display your CPU architecture, you can use the lscpu command. There is also some info in the ls hardware. Execution. When a program uses only CPU and memory, it is called processing or computing. When a program uses other parts of system, hard disk network or printers, it is called input-output. Input-output is much slower than CPU memory processing. As we can see, everything here is fast. If we have to reach outside, it will be much slower. Linux operating system. To use the hardware and write programs, we need an operating system. One of the most common ones is the Linux operating system. Linux runs on most computers and has a big community and support. It also supports most of programming needs and is free to use and modify. Linux has two main parts, the kernel and the user space. Various distributions of Linux like Debian, Ubuntu, or Red Hat take the kernel, customize it, and provide the user space. To explore the system, we will use and learn the shell, also called the terminal or the Xterm. We can see the overview of the system here. User space, it's all the desktop environment, the shells, etc., and the kernel does everything else for us. Kernel. Kernel is the heart of the system and provides all services needed by the user application. It is located in the boot directory together with other needed boot files. To see the system information, we can use the uname command. If you're new to manuals, please see the manual for itself. Console. Console is the main interface to the Linux kernel. It allows executing system calls. To log into the console, press Ctrl Alt and 1. To go back to the desktop environment, press Ctrl Alt and 7. This is how the console looks. Console and the more modern user space replacements like pseudo-terminals run the shell. Shell provides a more robust environment to run programs and manage the system compared to the basic console. As we can see, this would be a shell, or Xterminal. For more details about the console, please see this link. System calls, main services or functions exposed by the kernel. They can be called from programs, scripts, or interactive shell. We will use system calls in programs in the last chapter. Drivers. Linux drivers usually just work, so we don't have to deal with them, unless you want to program the drivers themselves. They can be part of the kernel static or modules loaded dynamically. Device files. Kernel or driver will usually create corresponding device files in the dev directory. These are special files that allow communication with the drivers using the basic file interface. A special UDIV program is handling the dynamic devices, plugged in after the system boot. Devices can be uniquely identified by major and minor numbers. Major number points to the particular driver, while minor number points to a particular device for that driver. These are the major and minor numbers. Device types can be character or block, marked by the first character in the ls output. We can see character and block device. Character devices handle data character by character, in example keyboard, printer, or USB. Block devices are handling blocks of data and also providing the buffering. These are usually the hard disks. In the above example, the SSD disk is represented by 4 block devices and 1 character device. A character device may serve for disk health monitoring. Block devices represent the whole disk and particular partitions. These are the partitions, this is the whole disk, and this is the character device for monitoring. Hardware commands. To inspect your hardware, you can use one of these commands. Processing. Linux is a multi-user and multitasking processing system. It abstracts computing into the processes. A process is a running program and is managed and scheduled by the kernel. Multiple processes are multiplexed or switched in a way it seems that they are running at the same time. Of course, this may be true if CPU has multiple cores. If there is only one core, programs can still spawn multiple processes. If, in example, a process is stuck on input-output, the other can continue using the CPU. This would seem like parallelism. We can see that the scheduler will switch between the processes. Process properties. Since a process can start one or many other processes or threads, each process will have a parent process. The first process in the process tree is the init program, and it has a parent with the ID 0. Processes also have other properties or attributes. In example, they will have a user, ID, parent ID, how much CPU time they used, how much memory, and the command that was ran to start them. File descriptors. File descriptors are process unique identifiers for a file or other input-output resources, like pipes and sockets. These are usually positive integer numbers. By the POSIX standard, each process should have 3 default descriptors defined. An example, 0 for the standard input, 1 for the standard output, and 2 for the standard error. These input-output streams allow processes to read and write data in a standard way and can be tied to any other processes or files. In example, When a program runs in a shell, its standard output is connected to the shell standard input. Or if we want to redirect program standard output to a file, we can use the redirection operator. With state, processes can be in a defined number of states. The most common state is the running state. Listing processes. To see the processes that are running on your computer, you can use the ps command. For a more interactive session, you can use the top command. Inter-process communication. Linux provides many ways for processes to communicate with each other. Files. In example, we can just use the regular files for communication. Signals. Linux provides a way to send signals to processes. Programs can customize some of the signal handling. In example, to kill a process, we can send a termination signal. This is the process ID. We use the kill command. Network sockets. In example, client-server TCP/IP communication made by browser and web server on port 80. UDP is a less reliable communication method but can be used for some tasks. Unix sockets. File system is used for communication. In example, programs will use this file to communicate with each other. This is a special file and it's faster than the TCP/IP. Anonymous pipes. To pipe programs together, we attach one program's output into another program's input by using the pipe character. This is very useful to combine multiple tools together. For example, we can customize the ls output by filtering it through grep command. Named pipes. Named pipes are special files similar to anonymous pipes but are used from the file system by a name. Can be useful to avoid data writes to disk while processing. Shared memory. Child and parent processes can share memory. This is used more in programming languages for managing complex parallel computing scenarios. Memory map files. RAM can be used to store files for communication. Memory management. As we have seen, memory is just a map of addresses and values. Each process has a dedicated part of memory. Main types of process memory are stack and heap. Stack is fixed size and is used for function calls and its local variables. These are automatically freed. Heap has a dynamic size. Program need to allocate it and free it manually. It may or may not show it in the pmap output. This is an example of the process memory map. It will have stack part, shared libraries, it will have a heap, and also parts for the static data. The last is the program's text. Kernel memory will have the user space, kernel space, and some kernel stuff. Another feature of memory management is that there is a virtual memory address space. These addresses are logical and different from the real physical ones we discussed so far. Virtual memory allows Linux to, in example, use hard disk as part of memory if RAM is full. This is called swapping. Example of a process memory layout. If you use the pmap command, we can see how the process looks in memory. Network. When talking about networks, we may refer to computers as hosts, nodes, servers, clients, etc., depending on the context. On top of the network hard drivers, kernel provides the implementation of the Internet's TCP/IP protocol, and some others. This allows easy network communication via the socket interface. Sockets. Sockets are communication channels based on file descriptors and particular protocols. They allow bidirectional transfer of data between two nodes or programs. They are used similar to a file, read and write. Most popular protocols are IP and Unix. IP. IP protocol provides networking based on IP addresses. IP address is a 32-bit number that uniquely identifies each computer on the network. There is a newer version of IP called IP version 6, with 64-bit addresses, usually represented with hex in example. IP part of the kernel networking stack is responsible for correct routing of IP packets. These packets will have all the info needed by the routers. This is the structure of the IP packet by the standard. It will contain the TCP packet. TCP is a higher level protocol we will inspect in a minute. To inspect your local interfaces which represent your network hardware devices, run the IP address. The LO interface is a special one and it is used locally by programs and Linux kernel to communicate via TCP/IP. It can be used for testing, etc. The main interface is the Wi-Fi interface here and it will have an IP address. This number here is special, we will learn in a minute. Subnetworks. The IP network can be divided into subnetworks. For this purpose, the IP address is split into network and the host identifier parts. The number after / is the network bits number. In this case, 24. In example, 24 is used to tell 24 bits of this address are used to identify the network, and 25 is the 25th host on that network. The network part can be useful for grouping nodes, broadcasting messages, or network routing. Most common network is the local or LAN network. In this setup, router will have a local and a public IP address. Among others, the addresses in this range are reserved for private and local networks. This way, everyone can use local IPs without worries of collisions. The router will have a public IP and local IP. Locally, everything is broadcasted, so when a laptop sends a message, it will go to PC and the router. Router will then send the traffic to your ISP, and it will get routed until it gets to its destination. TCP provides a reliable stream-oriented full duplex connection between two sockets on top of IP, guarantees that the data arrives in order and retransmits lost packets, generates and checks a per-packet checksum to check transmission errors. TCP sockets can be used in two modes. Outgoing socket is the client, in example a browser. Listening socket is the server, or in example a web server. When creating a listening socket, you have to specify the port number. The port is a 16-bit number that identifies the application that is listening on that network interface. In example, in the combination of IP and port, host IP is this, and the port is 80. Port numbers usually follow a standard, but this is not enforced as you can run anything on any port. Some common ports are 80, 443, and 22. Of course, you can only run one particular application on one port. Outgoing sockets will use free and unused ports. In example, your browser may connect through port 56245 when accessing Google.com. If you look at the TCP packet, it also has a bunch of headers that it uses to make the communication reliable, and it also has the application data. TCP flags determine the type of the TCP packet. In example, synchronize, acknowledge. TCP IP. TCP and IP work together to provide the networking, relying on the underlying frames. Frames are the lowest level of the network stack and contain the IP packet. Most common are Ethernet or Wi-Fi frames. These frames work on a MAC address level and are used for LAN communication only. As we can see, application data is in the TCP packet is in the IP packet, and IP packet is in the Ethernet frame. All of this is just a number of bits going through a wire or wirelessly. TCP will make a connection in 3 steps. This is called a 3-step handshake. After a server opens a listening socket, the client will establish the TCP connection in 3 steps. First, it will send a SYN packet with a sequence number which is randomly generated. The server will take this sequence number and acknowledge it by adding 1 to it. It will also send its own sequence number, which clients will then also acknowledge. After this, the connection is said to be set up. In this image, we can see the client will send a SYN packet, server will send a SYN acknowledge, then the client sends acknowledge, and then it can send the data. Data is sent in the PSH packet. To close the connection, a FIN packet is used. If you look at an example, TCP dump command will allow us to see the traffic. If you look, this is the establishment of the connection, the SYN, SYNACK, and ACK, and then the data is transferred. As we can see, this is the HTTP protocol. And then in the end, they will send the FIN packet. DNS. To translate domain names into IP addresses, programs can use resolvers, which use the Internet DNS servers. An example, if we use the nslookup command for the Google.com, we'll get its IP. Resolvers will try the local cache before querying the predefined Internet DNS providers. When you buy a domain from these entities, you can define for which IP will it stand for. You can also set and control the subdomains. You get IPs by your server hosting provider as part of the operating system's network interface configuration. Besides the dynamic resolution provided by resolvers, we can hardcode IP DNS name pairs in the host file. In example, we can set any IP and any name as we wish. File system. File system allows us to manage data using different types of storage. In example, disk, RAM, pseudo devices, etc. Most common Linux file system type is X4. Others include swap, NFS, etc. In Linux, all file systems are mapped onto the same directory structure. This structure is called the root file system and begins with a root directory, /. If we check this directory, it will basically host everything on our computer. The mapping process for particular disk or partition is called mounting. Usually, all the disks will be mounted automatically, but we can use the mount command to see and manage them. There is also a ls-block command, which will list all your block devices. Linux Virtual File System is an abstraction layer which provides common ways for programs to access different file system types. It also provides real virtual file system which can be read or written to. In example, proc, exposes the kernel process information. Proc is a replacement for the old sys directory. Linux directories overview. Linux has a bunch of directories. Let's quickly go through them. Bin, essential command binaries. Boot, these are the boot-related files. Dev, for files representing your hardware and virtual devices. etc, used for system configuration. Home, these are the home directories for the users. Lib, essential shared libraries. These are used by computer programs to include common functionality. Media can be used to mount pluggable USB devices. Mount can be used for temporary mount. Opt is used if you want to install custom packages, an example not available with your system's distribution. Proc. Proc is a virtual file system with process and system information. Root is the home directory for the root user. Run is used for runtime data for system processes. Sbin holds essential system administration binaries. Serve, data for services like FTP and web servers. Sys, kernel-related system files. Temp, this can be used for temporary files which will be cleaned after a while. User, this is a secondary hierarchy for user application and utilities. It will also have a lib and lib64 folders. Variable data such as logs and spol files will be in var. This is the actual compressed Linux kernel image. User space, shell. Although not part of the kernel, shell is a very important tool for every programmer. Shell is a robust front-end to console interface, and it is used to run programs and manage the system. We can also create a file with multiple commands and execute it. This is called a shell script. Shell also provides a simple key-value pairs called the environment, which can be accessed in programs or scripts. We can use the env to see currently set variables. To set custom variables, we'll simply say the name and the value. To make it available to all programs, we need to export it. Package Manager. Package managers are used for installing, removing, and managing software in the Linux system. Debian family of Linux distributions uses apt. Apt needs to know where to download the packages from. These servers are defined in the apt sources list. Other than location, we can configure the sections of the packages to use. Main and contrib sections are open source software, while non-free ones may use proprietary code, usually the drivers. We can define the sections we want to use here. For more details, see the manual. After any changes to the sources list, run the update command to refresh the removed data. Next, use the install command to install any available packages. First, refresh the data. In example, install hardware info. You can remove it later, or you can remove it and also purge the configuration. To list installed packages or particular files in the package, you can use the dpkg command. Graphics. By default, Linux uses Xserver for 2D rendering and Mesa for 3D. You may need to install proprietary drivers from the vendor, in example NVIDIA, if the default open source drivers don't work as expected. Again, to see the devices, use the lspci and ls hardware. Programming. Finally, we get to use this concept in some simple programs. Let's start with the assembler. In the past, on first operating systems, system calls were called with the assembler. Assembler is specific to the computer CPU architecture, in example AMD or Intel. System call numbers can be found in C header files, in example. Assembler is not used very often, but it is important to understand how it works. To use a basic system call, Linux says we need to put the number of the system call in the RAX register. Then we can also set RDI register to set where the output will go. In this example, standard output or the shell. And also we pass the message. Finally, we also set RAX register for the exit system call, which is number 60. To compile the code, we need to translate it into the machine representation. These object files have the O extension. Now, to compile it, we run this command. Now we have the hello O. We can see it is an executable file. If you try to open it, it will just be gibberish. After the code is compiled, we need to link it with a linker program. Linker ties all libraries and code references into a final executable. To link it, run this command. Finally, we have our output file, or our executable. If we trace the program calls with strace, we can see that it indeed calls write and exit system calls. If we run the strace, we will see it will call write and exit. Now let's see this in C. With assemblers, programmers made the C language. Unlike assembler, C is portable because Linux systems provide the same system calls, defined by the POSIX standard. This is the documentation for the system call. If we now write the same program in C, we can see it is much simpler. C compiler will compile and link the program for us. C will also make the same system calls as the assembler, together with other initialization and the library memory mappings. To compile and link, we can also run it the same way, and we can strace it. We can see that the C will run much more stuff besides the write and the exit. Shell. With C and assembler, programmers made the shell environment. Shell makes it easy to write and execute programs and manage the system. We can execute individual commands in the shell or write a script. Bash will also call the write system call and exit, among other initializations. We can see the write and the exit, among a bunch of other stuff. And finally, Python. With C and Shell, people made other programming languages for more robust features. One of those were interpreted languages, which don't have to be compiled to run. An example, Python. We can run the Python without compiling. We can also strace it to see what it does. We can see it will also call the write call and the exit. Besides interpreted languages, the graphical libraries started to emerge. This brought us the great age of the desktop environment. Please check the Python official docs. If you like the video, please leave a comment. Thank you for watching.